When you picture the massive gravitational forces at work during like the really early chaotic days of a young solar system, it's it's pretty easy to just imagine this purely destructive environment.
Oh, absolutely. Just total chaos.
Right, like you have these ancient colossal forces of gravity just swinging through space, acting like cosmic wrecking balls.
Yeah, that's exactly the image we've always had.
And the prevailing idea for, I mean, decades has always been that whatever gets in the path of a migrating gas giant is simply obliterated, just scattered into deep space or swallowed whole.
Yeah, the standard model of planetary migration definitely supports that view. Like when we look at a hot Jupiter.
Right, those massive gas giants orbiting scorchingly close to their host star.
Exactly. When we see one of those, we're basically looking at the aftermath of a really violent journey because these giants, they don't form that close to their stars.
You just can't, right? It's too hot.
Right. They form much further out in the protoplanetary disk, out where there's enough cold material, ice and gas, to actually build up a massive core.
Oh, okay, so they start far away.
Yeah. And as they grow, they open up this massive gap in the disk of gas and dust. And then through a process we call type 2 migration, they lose angular momentum and slowly just spiral inward toward the star.
And as they spiral inward, I mean, their gravitational influence is just so immense. They basically act as a giant broom.
A very heavy broom, yeah.
Right, just sweeping the inner solar system completely clean. So any rocky worlds or like smaller ice giants that happen to form in those inner orbits, they just get gravitationally kicked out of the system entirely.
Which is why astrophysics has long operated on this assumption that hot Jupiters are, well, the ultimate solitary bullies.
Solitary bullies, I like that.
Right. They demand the entire inner solar system to themselves. Nothing else is allowed to exist there.
Which brings us to the actual mission of our deep dive today. Because we are looking at a fascinating piece of space news that was just published May 22, 2026 in the Astrophysical Journal Letters.
Yeah, via technoscience.net, which is just an incredible find.
Truly. We are investigating a distant solar system that is completely fundamentally breaking those established rules of planetary physics.
It really is. The TOI 1130 system is it's a profound anomaly.
It totally shatters that solitary bully paradigm, right?
Completely.
Yeah.
It forces us to look at the mechanics of planetary migration in an entirely new way.
Okay, so let's get into the target. We are looking at a system 190 light years away, and this was actually initially flagged back in 2020 by Chelsea Huang, who was at MIT at the time.
Right. She was analyzing data from NASA's TESS satellite.
And TESS, for those who might not know, is a transit photometry mission. Basically, it just stares at massive patches of the sky looking for these tiny periodic dips in starlight.
Exactly. The dips that happen when a planet crosses right in front of its star.
Right. So Huang found the expected signature of a hot Jupiter in this system, which got cataloged as TOI 1130c.
But the data showed something else in that inner system, too.
And that's the shocker. Right. Because based on everything we literally just talked about, how destructive a migrating hot Jupiter is, this other thing simply shouldn't be there.
No, it really shouldn't. The data revealed a second, much smaller dip in the star's light.
Sitting right there in the inner system.
Intimately close to the host star. Just sharing that incredibly tight space with the massive gas giant. In this second dip, it's a mini-Neptune.
A mini-Neptune. I mean, it's wild. This inner companion designated TOI 1130b somehow survived the violent inward migration of that hot Jupiter.
Which is just, it's mind-boggling.
Okay, let's unpack this for a second, because I want to make sure we're really getting how weird this is. It's like watching a massive bulldozer clearing a path on a highway.
Right.
Just destroying everything.
Okay, yeah, good analogy.
But somehow, there's this tiny smart car just driving right in front of the blade, completely unharmed. The bulldozer came through, yet the smart car survived.
Yeah, that is exactly what it's like. Chelsea Huang herself was completely taken aback by it.
I actually have her exact reaction here from the sources. She said, this system is one of a kind. Hot Jupiters are considered solitary, yet here an inner companion has survived.
You can almost hear the disbelief in her quote.
Definitely. But, just seeing the anomaly in the test data, just proving the smart car there isn't enough, is it?
No, not at all. We can see the two planets there now, sure. But to prove how the mini-Neptune survived the migration, we first have to prove that it actually migrated in the first place.
Right, because maybe it just formed there after the fact.
Exactly. We have to unpack the planet's history. And in astrophysics, the absolute most reliable record of a planet's history is its chemical composition.
So we need to know what it's made of.
Right. If scientists could determine exactly what this mini-Neptune was made of, They could determine exactly where it originally formed in that early protoplanetary disk.
Okay, so this brings us to Sagata Bharat and his team at MIT. They are the ones who basically set out to read that chemical history.
Yes, and to do that, they needed the serious observational power of the James Webb Space Telescope.
The JWST. Now wait, here's a question. If we already know exactly where these planets are, like we have the coordinates, why is it so hard to just point a telescope at them?
Oh man. I mean, it sounds simple, right?
Right, like just point the camera and take the picture. I think it's easy for us to take an instrument like the JWST for granted and assume we can just look wherever we want, whenever we want.
Oh, absolutely not. Observing this specific duo was an incredibly delicate, incredibly high-stakes stakeout. The challenge basically comes down to a phenomenon known as transit timing variations, or TTVs.
TTVs. Okay, break that down for us.
So when you have a single planet orbiting a star, its orbit is generally this very predictable Keplerian clockwork.
Right.
You know, it will transit the star at the exact same interval every single time.
Like clockwork.
Right. But TOI 1130 is not a single planet system. You have massive hot Jupiter and a mini-Neptune orbiting incredibly close to one another.
So they are constantly interacting gravitationally.
Exactly. It's what we call an N-body problem.
Mhm.
Every time they pass near each other in their orbits, the massive gravitational pull of the hot Jupiter accelerates or decelerates the mini-Neptune, and vice versa.
They're just constantly tugging on each other.
Yeah, and those mutual gravitational kicks mean their orbits are constantly wobbling, the planets speed up and slow down. Because of this, you just can't set your watch by their transits.
So a transit that happened on a Tuesday last month?
Might happen hours earlier or later than expected this month.
Oh, wow. Okay, I see the problem. And when you're dealing with the James Webb Space Telescope, time is arguably the most fiercely contested scientific resource on the planet, right?
Oh, without a doubt. The thermal constraints of the telescope, the angular pointing limits relative to the sun, the sheer demand from the global scientific community. I mean, it all means you don't get to just stare at a star for a week and wait for the planet to eventually show up.
You get a rigidly defined, incredibly narrow time slot.
Exactly.
Yeah.
Bharat's team had exactly one single window to catch this transit. One shot.
And Sagata Bharat actually summed up the pressure perfectly. He said, we had to aim right. Because if the mini-Neptune's transit happened even a few hours early because of that gravitational wobble,
They would point the telescope at the star, capture nothing but baseline starlight, and the entire observation would just be a total loss.
a complete waste of JWST time. No pressure. So how did they solve it? How did they know exactly when to look?
To pull it off, the team brought in Judith Korth from Lund University. She specializes in orbital dynamics.
Oh, so she's the math genius in this story.
Basically, yeah. She utilized historical TTV data from previous observations and built this highly sophisticated mathematical model.
So she mapped out all the wobbles.
Right. By mapping out the complex Hamiltonian mechanics of their gravitational tug-of-war, her model integrated all those past wobbles and predicted the precise, adjusted moment that the mini-Neptune would cross the star.
And the model was flawless, right? They caught the transit perfectly.
They did. It was a massive success just to catch it.
But I want to dig into how they actually extracted the chemical history from that transit. Because the mechanics of transmission spectroscopy are just fascinating.
It is such a cool technique.
Right. So when the mini-Neptune passes in front of the star, the JWST isn't just measuring the dip in brightness to prove the planet is there, like tested.
No, it's doing something much more complex. It's actually analyzing the starlight that filters through the very edges of the planet's atmosphere.
Right, the Terminator line, the boundary between day and night on the planet.
Exactly. As the starlight passes through that incredibly thin atmospheric annulus, that ring of air, the photons interact directly with the molecules in the planet's atmosphere.
And different molecules react differently to the light.
Right, they have unique molecular bonds, and those bonds vibrate at specific frequencies. So when a photon with a frequency that perfectly matches the vibrational mode of a specific molecule hits it,
The photon gets absorbed.
you got it. The photon is absorbed.
So when the JWST's spectrographs capture that light, they basically spread it out into a spectrum, like a rainbow. And scientists are looking for the missing light.
Yeah, the dark bands where specific infrared wavelengths were absorbed by the atmosphere.
Those missing wavelengths are the literal fingerprints of the molecule.
The exact chemical fingerprints, yeah.
And the fingerprints Bharat's team found in the atmosphere of TOI 1130b were startling.
They really were.
They found a high concentration of heavy elements. And in this context, we aren't just talking about, like, a slight enrichment of metals, they found definitive signatures of water vapor, carbon dioxide, sulfur dioxide, and methane.
It is an incredibly rich, volatile chemistry for a planet located so deep in the inner solar system.
Okay, wait, let's pause on that because here's where it gets really interesting and where the puzzle pieces sort of snap together.
Let's hear it.
If this mini-Neptune is orbiting intimately close to its star-like, right next to a scorching hot Jupiter, the equilibrium temperature has to be just scorching.
Absolutely blistering.
Right. And yet it is packed with volatiles like water, CO2, and methane. Shouldn't those have just burned off or never even formed in that heat?
That is the perfect question. Based on the temperature gradient of a young solar system, those elements simply cannot condense into solid building blocks anywhere near the star.
Because the ambient heat would vaporize them instantly.
Instantly. You're touching on one of the most fundamental boundaries in planetary formation. The frost line or the ice line.
The ice line. Okay, explain that for us.
So in a protoplanetary disk, the inner region near the young star is dominated by what we call refractory materials.
Right, the stuff that doesn't melt easily.
Exactly. Silicates, iron, heavy metals. They have incredibly high melting points, so they can remain solid in that intense heat near the star. But volatiles, like water and methane,
They just remain as gas.
right, they can't clump together to form the core of a planet. A planet forming in the inner solar system is going to be rocky and dry, like Earth or Venus.
Okay, so to get massive amounts of water, ice, and frozen methane to actually stick together and build up a planetary core.
You have to go far out into the disk,
Hmm.
well beyond that ice line, where the deep freeze of space allows those volatiles to actually freeze into solid grains.
Oh, wow. Okay, so the presence of those specific volatile fingerprints in the JWST data, the water, the methane, that's the smoking gun.
It's the undeniable proofs the team was looking for. TOI 1130b could not have formed in its current location. The physics of the protoplanetary disk just completely forbid it.
So the mini-Neptune must have formed way out in the deep freeze of the outer solar system, accumulating this massive envelope of ice and heavy volatile materials.
Exactly, which means we now have the full trajectory of this system.
Right. So what does this all mean? It means the massive hot Jupiter formed out in the cold dark.
Yep.
And the mini-Neptune formed out in the cold dark.
Also true?
Then the disk dynamic shifted, and the massive gas giant began its destructive Type 2 migration inward, acting as that giant gravitational wrecking ball we talked about.
But instead of scattering the mini-Neptune into the void or kicking it out of the system,
It dragged the smaller planet along with it.
it did. There's actually a really beautiful artist's impression of this by Jose Luis Olivares at MIT.
Oh, I saw that. It's stunning.
It really captures it. You see these two massive worlds, born in the freezing outer limits, migrating hand in hand toward the blinding heat of the inner system.
Hand in hand. But, okay, this forces a massive question, and it brings us back to the original mystery.
Why didn't they crash into each other?
Exactly. If they are migrating together and the gas giant is actively perturbing the orbits of literally everything around it, how did the mini-Neptune survive the journey? Why wasn't it swallowed by the Jupiter or just flung directly into the star?
Well, the survival mechanism isn't a physical barrier. It's a mathematical one.
Hmm.
They survived because they became locked in a mean motion resonance.
Orbital resonance. Okay, this is where the physics of the system go from completely chaotic to, like, highly choreographed, right?
Very much so. The observational data confirmed that the mini-Neptune completes one full orbit around the star in almost exactly 4 days.
4 days.
And the hot Jupiter completes its orbit in exactly 8 days.
Oh, wow. So they are locked in a perfect 2.1 ratio.
A perfect 2.1 resonance.
Okay, to visualize this, I always think about coupled pendulums.
Oh, that's a good way to look at it.
Right, like if you put two separate metronomes on a shared movable board, they will start out ticking totally chaotically, right? At totally different times.
Yeah, totally out of sync.
But because they are sharing energy through the board they're sitting on, the motion of one metronome slightly influences the other. And over time, they will physically force each other to sync up, swinging in perfect, predictable harmony.
That is a fantastic analogy, actually.
Mm-hmm.
And it translates directly to orbital mechanics.
Really? How so?
Well, in this case, the shared board is their mutual gravitational attraction. As the hot Jupiter migrated inward, it approached the orbit of the mini-Neptune. And initially, yeah, their gravitational interactions would have been super chaotic.
And like the out-of-sync metronomes.
Exactly. But as their orbital periods approached that 2.1 ratio, the gravitational kicks they exchanged became periodic and cumulative.
Because the inner planet orbits exactly twice for every one orbit of the outer planet.
Right, so they meet at the exact same relative location in their orbits every single time. The gravitational kick happens at the same spot.
Oh, I see. And that periodic kick acts as an active, self-correcting, stabilizing force.
Exactly. Think about it. If the mini-Neptune slightly accelerates and its orbit begins to widen.
Which would normally put it on a collision course with the hot Jupiter.
Right. But the precise timing of their resonance means the hot Jupiter's gravity pulls backward on the mini-Neptune during their conjunction. It saps a tiny bit of orbital energy from the smaller planet, forcing it back into its tighter orbit.
That is incredible. And conversely, if the mini-Neptune slows down and starts falling closer to the star,
The hot Jupiter pulls it forward, adding angular momentum and pulling it right back to safety.
so they are actively exchanging angular momentum to keep their orbit stable.
They are. The very gravitational force that usually acts as a wrecking ball to scatter planets is, in this specific configuration, acting as an invisible tow bar.
An invisible shield, just keeping them at a perfectly safe, mathematically enforced distance throughout the entire migration process.
It's just brilliant. And if we connect this to the bigger picture, the implications of this 2.1 resonance go far beyond this single star sister.
It totally rewrites the rulebook.
It demands a fundamental revision of how we search for exoplanets. Because for decades, the assumption has been that finding a hot Jupiter means you just stop looking for other planets in that system.
Right, the neighborhood was assumed to be totally sterile, swept clean.
But TOI 1130 proves that if the orbital dynamics fall into these specific resonant mathematical ratios, smaller, volatile-rich planets can absolutely survive the journey.
They can hold on to their atmospheres, their water, their carbon, and endure the extreme environment of the inner solar system.
Exactly. We now have a clear mandate to revisit previously observed hot Jupiter systems. We need to apply these highly sensitive transit timing models to see if there are other hidden survivors.
Other mini-Neptunes just masked by the glare of their host stars.
Right, locked in these resonant survival dances. It really suggests that planetary architecture is far more resilient than our early models accounted for.
It fundamentally changes the narrative of the cosmos for me. I mean, we began this deep dive talking about the universe as a place of binary destruction, right?
A chaotic billiard table.
Exactly, where massive forces simply obliterate anything in their path. But the physics of TOI 1130 reveal something far more elegant.
It really does.
Beneath the extreme gravitational violence of a migrating gas giant, there is a hidden mathematical harmony capable of taming that chaos.
The math saves the day.
It does.
Yeah.
And it leaves you wondering, if the very forces we assumed were the ultimate cosmic wrecking balls can actually lock planets into synchronized, self-correcting protective orbits, what other seemingly destructive phenomena out there might actually be creating perfectly balanced, safe havens for strange new worlds?
It forces us to respect the sheer complexity of orbital mechanics. The universe doesn't just destroy, it organizes.
It organizes beautifully. Thank you all for joining us on this deep dive into the TOI 1130 system. Keep looking up, keep questioning the models, and we will catch you on the next one.